What's up guys, Pete here, and welcome back to Proto-Write Productions. Today we have a very exciting episode for you as we actually fabricate and assemble our full structural frame and motion assembly for our universal test machine. I know this video has been a long time coming, so I wanted to start out with just showing you straight out, yes, it's here, we are making some genuine progress, it is here in the flesh. But let's now jump back in time a little bit and show you how we got here. First things first, let's head on over to CAD and show you exactly where this thing came from. All right, here it is in its very unfinished, unrefined glory. This is probably about 85–90% done. As we go through this, you'll see that most of the structural components are here, but there are definitely a few really critical items that I still need to refine before this can really be called finished. This is very much still a prototype design. There's a lot of changes I already want to make about this, but at least for right now, this was good enough that I could start fabricating parts, and this gives me a test bench that I can start playing with. That being said, let's dive into this and just start taking a look at some of the broad strokes of the design that I've settled on. Now, if you watched the last video in the series, you're going to recognize a lot of the design cues that I've borrowed from other creators and kind of rolled into this design here. I tried to pick and choose kind of the best attributes of all of them that would meet our requirements overall. First, let's start with just a high-level overview of what we're looking at here. Immediately, right off the bat, you're going to notice that this is very similar to Stefan's design for his open pull machine. It's a very similar in concept where you have these two different lead screws supporting the machine frame here, and then we're pulling on the central crossbar to actually stretch our specimen. The main difference between my design and Stefan's, besides obviously mine is not made of wood, is that I've moved the position of the load cell to the top plate up here, and what that means is that all of the loads are carried just by the top plate and the crosshead. This bottom plate, while it does help with alignment and some aspects of the structure of the system, technically you could do away with this bottom plate entirely and everything should still function. Simplifies the design a little bit, and means we can spare some cost on this bottom plate down here. Now, I've also gone and decided to use not only the lead screws, but also a set of smooth guide rods on the left and right here to provide a little more stability for the system as a whole. I went back and forth on this decision, and I'm a little worried this might over-constrain the assembly, especially with like hand fabrication tolerances that we're going to be working with. But for right now, I like having them. I know that I can meet the tolerances I need for them to work effectively, and I think this will be a good choice overall. I was a little worried about some of the racking and twisting forces the system might see if anything's ever off axis, which it's going to be eventually. And so I wanted to add a little bit more structure here. And so for now, I'm going to add these guide rods. If it ends up that they're not needed, the whole machine gets a little more compact. The BOM gets a little bit shorter and cheaper. So not the end of the world if we decide to remove them. But for right now, I think I'm going to leave them. Something else that I went back and forth on a fair bit was how I wanted to actually build the structural frame around this tester. And frankly, I'm still kind of going back and forth on it a little bit. What I have here is actually two different solutions kind of crammed into one just to play with a couple of different options here. But ultimately what I've settled on for now is using some 2020 extrusions inside of the actual top and bottom plate. So you can see they mount between the two and they're held inside the edges of the frame currently. I was toying with the idea of mounting these external to the frame, which is why we have these little L brackets here. But for right now, I don't think it's going to make a ton of sense. Functionally, I really like the solution that I have right now. The only real problem with this is that these ends are currently going to be just factory saw cut ends, and so they're not going to be square or flat or straight in any stretch of the imagination, and frankly, they may not even all be the same length. In fact, I can pretty much guarantee that they're not. So you can run into some issues where you're going to kind of rack and torque this frame in weird ways when you go to clamp everything down if these aren't all the correct length. That being said, the couple of batches that I've gotten so far have been fairly consistent in length, and because I have so many, in this case it's going to be 6, 3 on the left side and 3 on the right side, as long as you tighten them all down at the same time and they're not crazy out from one another, it shouldn't really influence the overall frame too much here. I think structurally it'll be just fine, it'll hold everything nice and rigid, but it won't put any weird twists or bends into the frame as a whole and get things too out of skew to the point where it actually can't move anymore. We're going to try it this way and see how it goes. If I do run into some real issues trying to get everything fit up, then we may go back to this option where they're held on the outside of the frame. That would mean that we're not constrained by the kind of cut ends of these pieces anymore, which would simplify assembly in a couple of ways. But like I said, for now, we're going to try it this way with the beams on the inside of the frame, and we'll see how that goes during assembly. Now, the various fixtures that we need to do our various different tests is still one of the big open items for me currently, and that's going to be a problem that I need to solve relatively soon here. You can see at the moment what I'm playing with is an option for 3-point bend testing, and this is actually a frame that I've used for manual 3-point bend testing in the past, and I think this general structure should work pretty well, but don't pay too much attention to this right now. This is definitely subject to change. I have to figure out the whole ecosystem for how we want to attach our different fixtures here, but for now, this is just kind of a placeholder. The reason I don't have a set of grippers here for tensile testing is because, frankly, I have no idea how I want to tackle that right now. Designing a set of grippers that are going to be cheap, strong, easy to manufacture is kind of a challenge, especially at some of the loads that we're going to be dealing with here. There's a bunch of different ways we can solve that problem, but doing it in a way that, again, is cheap, efficient on material usage, and doesn't require any advanced manufacturing techniques is a little challenging. Like I've said a couple of times before, there's a pretty good chance that whatever we come up with for these final gripper designs, they're probably going to have to be machined. It's not ideal, but if we put together a group buy or we can outsource them in some way, we could still make this fairly accessible to most people. But this is definitely one of the larger problems that I'm trying to solve right now. So if you have any ideas what I can do with that, please let me know. Now for our DRO, the attachment here is fairly straightforward, though you'll notice I have a couple of loose ends that I need to tie up here. The included brackets that come with these DRO scales should work totally fine for mounting to the bottom plate down here, but unfortunately they're not quite the right length to attach to the top plate. So we will need to print some type of little spacer in here. That should be fairly straightforward. Then for attaching the actual slide itself to our crosshead, that will need another printed part here. Again, fairly simple, fairly straightforward, so nothing too complicated yet. We will need to make sure that this is aligned fairly straight and square with the rest of the frame, because what you don't want is to put a bunch of tension in this. If this were, say, at a weird angle relative to the rest of the frame, as this crosshead moves up, it's going to cause issues where you're potentially going to, bind up or even break your DRO. So we will want to make sure that this is fairly aligned with the rest of the frame. The stock brackets that come with these DROs do have slots in them, so we should be able to pretty easily adjust this to make sure everything runs nice and true. There's still a lot of work that I need to do as far as DFM and just general assembly help here. One thing that I know I want to work on is standardizing my hardware. I have a mix of like M3, M4, M5, M8. It's a lot of different screws, a lot of different lengths. So there's definitely a lot of work that I still need to do there, but that's going to come way further down the line once we have a lot of the bigger kinks sorted out. Another kind of open question here is, what the heck am I doing with all the electronics? There's not really any consideration for an electronics housing right now, or wire routing or anything like that. It's all an open frame, so there's plenty of options there, but I haven't really finalized any of them. There's also things like limit switches for end stops that I know I'm going to need, I know I'm going to want them. I've got one just kind of floating in free space right now. Those are all things that we're going to have to figure out, but for right now, I don't need to worry about it to at least get a functional prototype up and running. Now let's take a closer look at our motion system here, because there's a couple of things that I want to point out. I want to try and use standardized components, just off-the-shelf parts wherever possible, and we're going to do exactly that here. We're going to borrow from the already very fleshed out ecosystem that's used for ball screws, and use the fixed and floating end bearing mounts for our lead screws, and that's what you see here. Now, there are some little tweaks we're going to have to make because we are using just a straight lead screw as opposed to a ball screw in order to make them actually work with this style of bearing blocks. But it's still a lot less work than having to manufacture these bearing blocks totally from scratch, and it should be pretty cost effective. Starting at the top here, this is the portion that's going to be fixed to our top plate, and this is where our fixed bearing block is going to be. This is going to come pre-installed with angular contact bearings that'll work great for taking up both the radial and axial loads that our lead screw is going to see. The bearings inside this block need to have a preload applied to them, and if you're using a ball screw, well, that screw would have a shoulder turned down on one end of the shaft down here, and a finer pitch thread at the top that you'd be able to thread a nut on to clamp everything down and preload those bearings. Now, obviously, we're just using a straight lead screw, which means it has none of those extra features turned onto it. So to try and emulate that, here's what we're going to do. Instead of a shoulder being turned onto the shaft, we're just going to use a shaft collar, and hopefully this can bite down hard enough that the preload and all the force from the actual movement of the crosshead doesn't shift this down, but we're going to have to look at that. Then to actually apply our preload, we're just going to use another Acme nut at the top here. Now, unfortunately, finding a traditional hex nut but with an Acme screw is a little bit hard, so we're just going to use the same type of Acme nut that you'd use to actually transfer motion. It'll work totally fine. It's the same thing functionally. It just means it's going to be a little bit harder to tension, but a pipe wrench, a pair of vice grips, or an actual pin spanner will work just fine in this case. We've got some standoffs here to make sure that our shaft collar doesn't actually rub against the top of our top plate. We've got our Acme nut that's going to transfer the motion to our crosshead, and then all the way at the bottom we have our floating bearing block down here. Now there's one more change that we'll have to make, and that's that the standard set of bearing blocks that you'll get, this particular one is going to be sized incorrectly in the bearing for our size of shaft. So unfortunately we will need to pop out this bearing and replace it, but fortunately that's a very easy task to do, and the bearings are very affordable. Overall, I'm hoping that this stack up should be fairly economical, fairly easy to assemble, and hopefully very functional. That's kind of the main thing here. I think this should meet all of our requirements. Obviously, there's still a lot of design decisions yet to be made, but for now I think we've got more than enough to start fabricating our first functional prototype, which is really going to be the fastest way to learn about how the system performs overall and any changes that we need to make. So let's go crack open that box from McMaster Carr and get fabricating. Okay, so I know that this whole time I've been saying I don't want you to need fancy equipment to make this, and yet here I am going over to my Bridgeport. But I promise I'm just using it as a glorified drill press here. We only need drilled and tapped holes in these plates. You could absolutely lay out all these holes with a caliper and a center punch instead of a DRO and an edge finder. And you can drill these holes on a drill press or even with a hand drill. Now in the future, I'm going to be doing more tolerance stack-up work to see just how sloppy we can be at these dimensions to accommodate more low-tech manufacturing options. But for now, just take my word for it, you can make this with simpler tools. The overall fabrication here is pretty straightforward. We're just drilling and tapping holes, so it's not rocket science. I'm just going through and spot drilling all my holes to keep my drill bits from wandering. A center punch would work just as well here. And if you thought that was fun, get ready to tap like 20 holes per plate. Now I've gone back and forth about changing some of these tapped holes to through holes. You could totally get away with using through holes in basically every location, you just need nuts and longer bolts. It would save tons of time in the fabrication stage and would cut costs if you did outsource these plates. The problem is that the assembly side of things becomes way more annoying. You're constantly needing 2 hands to tighten every bolt. I also think the cost of not needing to buy taps would probably be offset by the longer bolts and extra hardware if you did fabricate this entirely yourself. For now, I'm leaning towards leaving the tapped holes, but let me know what you think. If you do end up needing to tap this many holes though, please do yourself a favor and stop buying general purpose hand taps. Go and get yourself either a spiral flute tap or a spiral point tap. These are designed to push the swarf either ahead of the tap for spiral point taps, or pull it out of the hole in the case of spiral flute taps. They're stronger than general purpose hand taps, and more importantly, you're not constantly backing out the tap to break the chips. Even if you're not using them for power tapping, they make a world of difference for hand tapping. Here I'm using spiral point taps because all the holes are through, and you can see how it pushes all the chips out the bottom of the hole. It's so much faster because I'm not constantly reversing the tap. And it's just really satisfying to watch. Now, you should probably be checking for fitment before you drill the holes, but better late than never. Fortunately, everything looked good for both the bearing block and the base for the guide rod. That just leaves some quick chamfers on all the holes, a couple licks with the file to knock down those sharp edges. Don't worry, I found my deburring tool later. And that's the top plate done. And I promise, I figure out the whole auto exposure thing later. Now, really the only thing that's different about the crosshead is that it does need to be cut down to length. I'm using a horizontal bandsaw here, but obviously you can do this with a handsaw if you had to. It'll just take a bit longer. Dimensions here aren't that critical, so you don't need to be very precise. Now at this point, everything is pretty much the same as the other plates. Indicating the part in or doing layout if you're using a drill press, spot drilling your hole locations, and drilling all your holes. Now, since everything's the same from here on out, we're just going to skip ahead to... Alright, rescue mission time. Fortunately, carbide is harder than tool steel, and a 3/8 end mill is still smaller than my final hole size. So I should be able to just mill straight down, broken drill bit and all. That said, even a center cutting end mill like this one doesn't really like center cutting, especially when dead center is the hardest thing it's cutting through. So slow and steady is the name of the game here. Okay. Disaster averted. After that mild heart attack, I didn't really feel like filming the rest of the work on this part or the bottom plate, but I promise you didn't miss much. I did remember that I own a deburring tool though, so that was nice. With the plates done, that just leaves the couple of 2020 extrusions. This is where those spiral point taps really shine. They can power tap through holes like this like nothing. Like I mentioned earlier, for a matched set of these bearing blocks, they'll actually have a different ID for the fixed block compared to the floating block. In our case, for a 10mm lead screw, we want a 10 series set of bearing blocks, so BK and BF10 for the fixed and floating ends respectively. Unfortunately, the floating block in the 10 series only has an 8mm ID, so we'll need to have its bearings swapped out to fit our lead screws. Fortunately though, these are fairly cheap bearings to buy and pretty straightforward to replace. I've got a standard bearing designation for the correct size bearing on the screen now. All we need to do is pop out the old bearing, push in the new ones, and we're good to go. Next, we'll actually build our Z-axis assemblies. Now, like I mentioned earlier, ball screws will have a bunch of additional features turned on their ends to properly use these bearings. And obviously, we have none of those on these lead screws. So instead, we're going to improvise a little. What I settled on was using a 2-piece shaft collar to act as our shoulder, and another Acme nut to apply our preload. I'm a little worried about how much force these split collars can really take before slipping. It is just aluminum biting down on the hardened steel, so I'm worried it'll slip under higher loads, but only time will tell. Now, unfortunately, Acme hex nuts aren't particularly common. So, keeping parts availability and cost in mind, I've gone with the same kind of lead screw nut that you'd use to transfer motion. This should functionally work exactly the same, but it does mean we're going to have a little bit harder of a time to actually tighten this. You could totally just grab it with a set of vice grips, or you could buy yourself a pin spanner. Either will work just fine. Next, we're going to pre-install our bearing blocks for the cylindrical guide rails onto our crosshead. We're leaving everything loose at this point, and we'll tighten down everything later on once it's all in place. Next, we'll get our Z-axis assemblies roughly installed onto our top plate. This is also where order of operation starts to really matter. You're going to want to get those Acme nuts threaded onto the rods after you slip the rods through the top plate. Ask me how I know. You'll also want to make sure they're facing the right way around. Now we can start getting everything assembled. This is honestly where I still have a lot of work to do on order of operations and assembly fixtures. Here I'm building on top of a large surface plate, and this gives a nice consistent plane to set everything else from. I've gone ahead and printed some V-blocks here that will set the height of all of my lead screws. Now I've lapped the V-blocks in so that they're all within about 1/1000th of an inch of one another. Now I only needed to do that because I printed these sets on 2 separate printers. But normally these should be matched well enough right off most modern printers that you shouldn't need to adjust them at all once you've dialed in that height. And frankly, it's more important that they're the same height as each other rather than super close to our theoretical perfect height. Now, in theory, this should work great to align these screws in one axis inside of those holes. But unfortunately, this relies on the side of my top and bottom plates being known good datum surfaces, which they are very much not. On my stock, these sides are saw-cut edges, meaning that they are neither flat nor square with any other surfaces on these plates. Now this method still ended up working well enough, but not doing any machining on these sides is definitely going to be a limiting factor on assembly options. This would be much simpler if these plates were fabbed and entirely machined on all surfaces, meaning we could know those surfaces were reliable. You'll also notice that I needed to shim up the bottom plate to get the center line of the holes to the correct height. This was entirely avoidable if I had used the edge to set the dimensions for all my holes. Unfortunately, what I actually did was use the center line of the plates as my zero. While this makes things a little bit easier when it comes to machining things, it makes it much harder when it comes to actually aligning everything up for assembly. I'm keeping track of all of this for future GD&T notes on future drawings for these parts. Now at this point, I've already made an annoying mistake, and I didn't end up noticing until basically the end of the build. I've managed to put my bottom plate on entirely backwards. You see, these 2 holes here are for the DRO mount. You'll see a similar set of holes on the crosshead and the top plate, except those holes are both on the other side of those plates currently. Now, I could have just said screw it and drilled 2 more holes on the other side once it's assembled, but those extra 2 holes are going to annoy the heck out of me, so instead I just undid all of this work, flipped the bottom plate around, and put it all back together. Don't worry, I won't make you sit through all of that, but if you happen to catch that those holes magically flip by the end of the video, just know there was much swearing involved. Here I'm messing around with some 1, 2, 3 blocks to try and do something to the crosshead. I'm not really sure why, since I can just manually adjust one of the lead screws to get everything nice and square later before I mount the motors. So just ignore this. Did I ever tighten down those guide rods? Guess not. With all the major components mostly aligned, it's time to start snugging things down. Now, it's a little tricky to get around all the 2020 extrusions to actually get to the screws, but unfortunately, you kind of need to have them already in place before you can fully crank down on the other components. This is where I need to take a closer look at order of operations and the nitty-gritty details of the assembly. Even how you orient some of these parts makes it easier or harder to access things like set screws later in the assembly. At this point, it was getting pretty late, so I skipped over filming some of the final assembly steps here. But don't worry, in the future this will all be thoroughly documented in videos and written instructions. Here I've got the DRO installed, and I'm checking to make sure I've got good consistent movement. And it looks like everything's looking really good. All right, guys, that is going to do it. Our structural components are basically finished. Our motion components are finished. Everything works. I'm actually kind of a little bit surprised about that myself, quite frankly. Obviously, there were still a lot of things that we need to refine and dial in to make this assembly process and the manufacturing side of things more achievable for your average Joe in your kind of home shop. But that being said, I'm still really happy with where this turned out for kind of a first pass at things. There were a lot of question marks, at least in my mind, when I went through the initial design of this, but so far, most of those questions have been answered, and in most cases, those answers were good. There are obviously still a bunch of things we need to refine, and some major components that we still need to actually decide on, like how we're going to actually hold all of our specimens, but for right now, I'm really happy with where this is at. The motion system is nice and smooth, and I can actually run this by hand with very little force, and you actually have a fair bit of tolerance for angular misalignment before this thing gets bound up, so I'm actually very happy about that, even with these extra guide rods there, so that worked out really well. The frame feels really solid. Obviously, we won't know until we go to test it, but I think this thing will be able to hit that kind of 1,000-pound stretch goal of ours, but we'll have to see once we actually get some motors hooked up to it and some monitoring for the load cell. From here, the next big thing is going to be electronics, and that's the portion that I know the least amount and that I am the most concerned about. I have been doing a little bit of work in the background, and I have done control systems for all of these bits and pieces separately in the past, just not all working together at the same time. I've read load cells, I've controlled stepper motors before, I've read from the DRO, but integration hell is coming, and I know it's going to be rough. So bear with me as we figure out the electronics, but I think we'll make it through. We're also going to have to figure out a calibration system for the whole machine, and I'm not too worried about the DRO, but I am a little concerned about how we're going to calibrate that load cell. We need to apply several hundred pounds of load in a safe, controlled manner in a fairly tight, confined space. Heck, even if we do this outside of the frame, applying that load safely and carefully, but at a fairly high level of accuracy, is going to be very challenging. If you have any ideas, let me know. I got a couple ideas bouncing around that I want to toy with yet, but I think that's going to be honestly a bigger challenge than just the electronics in general, is figuring out that calibration process. All that being said, I'm still incredibly happy with where we're at for today. Hopefully these videos will start coming out a little more frequently, but obviously this is a big undertaking and I still have a day job to work on as well. But bear with me as we slowly trickle these out here because we are making some genuine progress. So thanks for sticking with me, guys. I really appreciate it, and I'll see you in the next one.